Alright, let's talk about everything in one video, all types of graphs. So we're going to cover everything in one video. So first of all, you know that this in the forward reaction, these are your reactants and these are your products. But in the reverse reaction, these are your products and these are your reactants, right? So just remember that in a forward reaction, these are your reactants, these are your products, but in the reverse reaction, these become your reactants, while these are now your products. So now let's talk about the initial situation before the first equilibrium is reached. So we know that initially when the reaction has just started, there's literally no products yet, right? It has just started. So there's literally no products, so they will start forming, right? So it will literally start from zero because initially there is no products, right? So as time goes on, the products will start being formed, so the concentration of the products will start increasing. So initially there will be no C, so let's just say C is this one, right? So there will literally be, or matter of fact, let's just say this is C. So let's say this is C. Let me just do this. I want it to be a little bit higher, right? And let's say this is D, right? So initially there is also no D, but as time goes on, D will start getting formed. So something like that, right? So now let's talk about our reactants. But first let me label this as planned. So this is D and that is C. So let's talk about our reactants. So now initially our reactants are high because it's the start of the reaction, right? Maybe we've got maybe 5 grams of this stuff and maybe we've got 7 grams of this stuff, right? So maybe we've got 7 grams of this stuff. So initially they are high at first, right? So as the reaction proceeds, they will start being used in order to make the product. So as they're used, they will start decreasing because they're used in order to make the product, right? So now let's talk about it. So notice that it's going to start off as high, right? It's going to start off as high and then it's going to start getting low, right? So it's going to start off as high because initially they were high, and then as time goes on, it's being used in order to make the product. So let's just say it reaches equilibrium at this point, right? So we're going to have a straight line. Yeah, I should have literally drawn straight lines for this one. I'm going to draw it. So let's say this is, let's just say this is maybe, let's say this is A. So let's say this is B. So B also starts off as high, and then as time goes on, it decreases, right, up until the first equilibrium is reached. So let's just do something like this. I want it to have this type of shape. So something like that. And then the first equilibrium is reached. So this is what we have. So if they ask you what happens at T1, you'll say this is when the equilibrium is now established, when equilibrium is now reached, right? So now, let's say all of a sudden at T2, we now increase the concentration of B. So it's a disturbance, right? So what you have to remember is that there is going to be a sharp increase in the concentration of B because it's unnatural. It's just what we've done. We've just increased it, right? So we're going to have a sharp increase like that, right? So now the system will oppose that increase in B by favoring the reaction that uses it as a reactant, which is the forward reaction. Remember, in the forward reaction, these are the reactants, these are the products. So it's going to favor the forward reaction so that this can be used up, so that it can be decreased, right? So immediately we know that the forward reaction is the one that is favored, right? So that this becomes the reactant. So if the forward reaction is favored, C and D are going to start rising because the forward reaction is favored. So it means the concentrations will start increasing, right? Up until a new equilibrium is established. So something like that. So the concentration will start increasing. Come on, let's just reverse that. So the concentration will start increasing. So this is what we're going to have, right? Up until a new equilibrium is established. So something like that. Okay, so let's just try one more time. So something like that. Okay, fine. I don't think it's going to be what I want. Let's just do this. So this will start increasing because the forward reaction is favored. So whatever is part of the forward reaction will start rising, right? The concentrations will start rising because the rate of the forward reaction is now increased, right? Because the forward reaction that is favored, right? So when the forward reaction is favored, we'll see a rise in whatever is part of the forward reaction, right? So the concentrations will increase. So now And this can be a graph for concentration. It can also be a graph for number of moles, right? So it's the same thing. Or even if they put mass, I wanted to put mass, but yeah, yeah, number of moles. So number of moles or concentration, right? This will be the graph. It will be the same situation. So when we've just increased the concentration of one, or if just increased the amount of one, there will be a sharp rise in that one that has been increased. And then we have to find out which one will the system favor, right? So the system will obviously favor the forward reaction, so therefore the forward reaction will start rising. But whatever is part of the reverse reaction will start decreasing up until a new equilibrium is established. So this, even though we did not do anything to A, because it's part of the reverse reaction, it will start decreasing until a new equilibrium is established. So I wanted it to be a curved line, not a straight line. So let's try this. So this is what we have, something like that. Yeah, something like that, right? So up until a new equilibrium is established. So this is what we have. All right, great. So what if B was decreased? Let's just talk about the situation where B was instead decreased, right? So let's just do this. Just before I continue, if you want to be tutored, whether it is online or physically, whether it is the situation where you're struggling in maths, or whether it is the situation where you're good in maths but want perfection, take a screenshot or save these details. Whether you're studying Cambridge, which is the UK curriculum, or whether you're studying NSC, which is the South African curriculum, or IEB, or native courses which start from N1 to N6, or any curriculum you're doing no matter which country you're at, we offer tutorials. We've got lessons and practice sessions 5 days a week. We also give you tests once a week so that we can check your improvement. If you're interested in knowing the prices, the video that contains the prices and the updated contact details, just in case these ones have changed, is found at the end of this video. Okay, so if B was decreased, there was going to instead be a sharp decrease from. So if they give you the graph from a sharp increase or a sharp decrease, you can tell what happened to the concentration, whether it was increased or decreased. So there's going to be a sharp decrease. So let's just say B was now decreased. So let's just say it was decreased. So there's going to be a sharp decrease, and then the system will now favor the reverse reaction so that this can be used as a product so that it can be formed, right? So then it means that whatever is part of the reverse reaction will have to start rising. So that's what we'll have. So this is what we'll have. So whatever is part of the reverse reaction will start rising, and whatever is part of the forward reaction should start falling. So whatever is part of the forward reaction starts falling. Come on, let's just, okay, fine, let's try one more time. So something like that. Let's see how it goes. Yep, it works. So something like that. And then whatever is part of the forward reaction will start falling. So up until a new equilibrium is established. So up until a new equilibrium is established. So this is what we have. So let's have something like that. So something like that. All right, great. So let me try and see if I can remove this stuff. Yeah, okay, fine. So therefore, let's just have something like this. Come on. So let me just fix it. So this is what we'll have. So now let's talk about something else. Let's say now this time we have decided to increase the temperature, right? So increase in temperature favors the endothermic reaction. So whenever you see enthalpy is negative, or whether you see they can present it as less than 0, or they can even present it like this, right? We know that okay, fine, let's just say it's minus something. So if we just say it as minus something, we know that the enthalpy is negative. So therefore the forward reaction is exothermic. So whenever the enthalpy is negative, the forward reaction is exothermic. But if it is positive, the forward reaction is endothermic. So this tells you what the forward reaction is. So the enthalpy is negative, meaning the forward reaction is exothermic. So increase in temperature favors the endothermic reaction, right? So let's talk about increase in temperature. So something like that. Forgive my handwriting. So if we increase the temperature, the forward reaction is okay, fine. the endothermic reaction is what will be favored, right? So which one is endothermic between the forward and the reverse? Because here it tells us the forward reaction is exothermic, it means the reverse is endothermic, right? So it means that whatever is part of the reverse reaction, since it's favored, is the one that is going to start having a steady rise. So this is the difference between the concentration graph and the temperature graph, right? So when it comes to concentration, when one of them is manipulated, we can immediately see a sharp rise or a sharp fall, right? So that's how we know it's concentration. And then what happens later tells us which one is favored, which reaction is favored, right? So now here, when it comes to temperature, there is no sharp rise or sharp fall. There is just a steady increase and a steady decrease, right? So the one that is favored will start increasing steadily. So because this is also part of the reverse reaction, it will start increasing steadily, right, up until a new equilibrium is established. So this is what we're going to have. So whatever is favored will start increasing steadily until a new equilibrium is established. And then whatever is part of the reverse reaction will start decreasing steadily because it is not favored, right? So so something like that, because the other one was instead what was favored. So something like that. So this is what we have. So something like that. So this is what we'll have, right? So up until a new equilibrium is established. So now, let's say instead there was a decrease in temperature. What would have happened? So decrease in temperature favors exothermic, since increase in temperature favors indo. So all you have to memorize is that increase in temperature favors indo. Then when we change something, you already know which one it favors. So it means the exothermic reaction will be the one that is favored, which is the forward reaction, because this tells us the forward reaction is exothermic. So it means that this one would have started increasing steadily, right, up until a new equilibrium is established. So something like that, right? So this would have started increasing steadily until a new equilibrium is established. So let's make it a curved line, something like that, right? Come on, so something like that. I don't know why it keeps doing this. Let's do this. So then we're going to have a new equilibrium being established, and here same thing, right? So something like that. And then as for the reverse reaction, since the other one, which is the forward reaction, was favored, the reverse will now have to be decreased, right? So this is what's going to happen, because the reverse reaction is going to, let me not go deeper, let's just leave it like that. So this is what we have, something like this. Yeah, something like that. Let's try one more time. So something like that, right? So now let's say so that's how you can tell that it's temperature that was manipulated. If this is a concentration or a mole graph, you can tell that temperature is the one that was affected because of that steady increase or steady decrease. If you see sharp increase or sharp decrease, you know it's the concentration of one of them that has been increased or decreased. So let's talk about pressure now. Let's say pressure is increased, right? So now let's talk about pressure. So increase in pressure favors the reaction that produces the lower amount of moles, right? So notice that here it's 2 plus an invisible 1 is 3, and then here it's 1 plus 1 is 2. So the forward reaction has the lower amount of moles. So if we increase pressure, the forward reaction is the one that is going to be favored. But when we increase pressure, the concentration of all of them, first of all, is affected, right? So this is how we know there is an increase in pressure. So there is an immediate sharp increase in all of them. Something like that. Come on. Okay, fine. Let's make it straight. So this is what is going to happen, right? And then which one is favored? The forward reaction is the one that is favored. So after that, after all of them has been affected, the forward reaction starts to rise because it's being favored, so that it can produce the lower amount of moles. So it's being favored, something like that. So the system will try to oppose the increase in pressure by favoring the reaction that produces lower amount of moles. So while these ones will start decreasing because they're not the ones that are favored, so they'll start decreasing. So something like that, right? So something like that. Let's just say there was now instead a decrease in pressure. What would have happened? So if there is a decrease in pressure, there is going to be an immediate sharp decrease in all of them, right? So something like that, sharp decrease, come on, sharp decrease in all of them, right? So we have a sharp decrease. Let's just do this, something like that, a sharp decrease in all of them. And then which one is favored? Decrease in pressure will favor the one with the higher moles this time, right? So let's do this. So the reverse reaction will now be the one that is favored. So it will start increasing up until a new equilibrium is established. So it will start increasing up until we reach a new equilibrium. So something like that, right? While the forward reaction will start decreasing. So this is what we'll have. So we're going to have something like this. Okay, not a straight line, but something like this. So the forward reaction will start decreasing, right? Because it's not the one that is favored. So something, come on. So something like that. Right, great. So now let's talk about the last thing pertaining to this. Yeah, so this is it. So this is when it comes to the concentration graph, but we have to be careful when it comes to the moles graph, right? So pressure, we can immediately see everything immediately gets affected when it comes to concentration, right? But if this is the number of moles versus time graph, for pressure it's a bit different. Everything's the same with moles and concentration, but for pressure it's a bit different. What is the difference with pressure? So let's say there was an increase in pressure, meaning that the forward reaction is favored since it produces the lower number of moles, right? So if it's the moles one, there will not be a sharp increase in the number of moles. It's only concentration that is increased, because when we decrease pressure, when we increase pressure, uh, we're decreasing the volume, right? So when it decreases volume, concentration is immediately increased. But when it's the moles graph, the number of moles is not immediately increased. The number of moles starts increasing steadily according to which one is favored. So since the forward reaction is favored, it means the number of moles would have started increasing steadily. So that's the only difference when it comes to the pressure one. When it comes to the concentration versus time graph, we can see that it affects everything. But when it comes to the number of moles graph, it just increases steadily like temperature, right? So if this is the moles versus time graph and you see a steady increase, you can't exactly tell which one has been affected between temperature and pressure. They will have to give you a clue. But if this is the concentration graph, steady increase is only for temperature, then the sharp increase in all of them would be for pressure. So then this will start decreasing because it's not the one that is favored. So something like that, it will decrease until a new equilibrium is established. So something like that, right? So this is what we would have. So yeah, up until a new equilibrium is established. So let's just say this was the mole graph and instead the pressure was decreased. So we know that the reverse reaction will be favored since it produces the higher amount of moles. So since the reverse reaction will be favored, the forward reaction will start going down because it's not the one that is favored. So it will go down steadily because it's the moles graph, right? If it was the concentration graph, we would have a sharp decrease everywhere. So this is what we'll have. So something, come on, let's do this, something like that. Okay, fine, let's just try one more time. So up until a new equilibrium is established. So something like that. Yeah, something like that. So while this one will increase steadily because it's favored, right? The reverse reaction is the one that is favored since it produces the higher amount of moles, right? Decrease in pressure will favor the reaction that will try to oppose that decrease in pressure by producing higher moles. So this is what we'll have. Alright, so now let's talk about catalyst. What will happen if a catalyst is added in the concentration or moles? Remember, all of them is the same if it's concentration versus time or if it's the number of moles versus time, right? All graphs are the same except when it comes to the pressure. When it comes to the pressure in the concentration versus time, if pressure is increased, there is a sharp increase in all of them, right? So there will be a sharp increase in all of them. But if pressure is decreased, there will be a sharp decrease in all of them, right? But when it's the number of moles versus time graph, so when it's now number of moles versus time, then increase in pressure will just have a steady increase in the side that produces the number of moles, and steady decrease, right, in the one that is not favored. Then decrease in pressure will have the opposite effect, will have a steady decrease in the higher number of moles and a steady increase in the, it will have the steady increase in the reaction that produces the higher number of moles and a steady decrease in the one that was not favored, right? So I hope you get it, right? So when it comes to concentration versus time, there is that sharp increase or decrease everywhere. But when it comes to the number of moles versus time, pressure does not have that sharp decrease or increase in the number of moles. It has a steady increase and a steady decrease. So let's talk about catalyst. What does the catalyst do? So what does it do? If I add a catalyst at T8, what's going to happen? Well, catalyst just speeds up the rate of reaction. So as for concentration, it does literally nothing. Everything will literally be the same. So we're just going to have it the same. So it's literally going to continue. So this is what we're going to have. Steady, like it's just going to be the same. Catalyst does not do anything. So let's talk about rates now. Alright, before I start with rate, I want you to first of all note that the rate graph is completely different from the concentration and number of moles graph. When it's very different from the concentration and number of moles graph, right? So the rate graph, even if we have got two reactants, we're going to have only one line that will represent the forward reaction. And even if we've got two products, we're only going to have one line again that will represent the reverse reaction. So if this confuses you, just ignore what I said, but I'm going to explain it, right? Just know we're only going to have two lines, one for the forward reaction, one for the reverse reaction. So it's completely different from the number of moles and concentration graph, right? So let's talk about how rates work. So there's one line for the forward reaction and one line for the reverse reaction, right? So let's first of all talk about the forward reaction. So remember, at the forward reaction, the concentrations of this are initially high, right? So they'll start being used up to form the products. So because the concentration of these are initially high, the rate of reaction will also be initially high, because according to collision theory, the higher the concentration, the higher the rate of reaction. But as concentration decreases, the rate of reaction will also start decreasing up until equilibrium is established. So this is what we'll have. So therefore, the forward reaction always goes down, right? Because the rate will decrease as time goes on, since the reactants are being used as time goes on. Alright, so now let's talk about the reverse reaction. So at the start, there is no product because it's just the start of the reaction. So because there is no product, there is nothing to reverse the reaction, right? There is nothing to form the reverse reaction. So notice that if there are no products at the beginning, the concentration is low. So if the concentration is low, if the concentration is zero, matter of fact, then the rate is also zero, because the rate depends on concentration. The higher the concentration, the higher the rate. The lower the concentration, the lower the rate. So it's going to start from zero. But as time goes on, the products will start being formed, and as the product starts being formed, the concentration of the product is increasing. And when the concentration of the products is increasing, we're now able to have a reverse reaction. So therefore, the rate of the reverse reaction will also start increasing. So this is what we will have. We'll have an increase, right? So we'll have an increase as time goes on, because the reverse reaction is now possible and the products are forming, meaning that the reactants for the reverse reaction has now higher concentration. The higher the concentration, the higher the reaction rate. So something like that. So up until a new equilibrium is established, so something like that. So we have an equilibrium up until T2. Let's just say T2, we've just made a disturbance, right? So now, let's say we have decided to increase the concentration of B. So what you have to memorize when it comes to the reactance graph is completely different from the concentration graph. when it comes to the reactance graph, you have to find out if you increase this is a reactant of which reaction. So remember, in the forward reaction, these are reactants, these are products, but in the reverse reaction, these are reactants, these are now products, right? So this is a reactant of the forward reaction. So whenever you increase something, the reactant of that you have increased, you have to find out what is the reactant of which reaction, right? And then whatever reactant is whatever the reaction that is a reactant of will be going to increase, right? So let me just try and explain it well, right? So this is a reactant of the forward reaction. Therefore, there is going to be a sharp increase in the forward reaction, right? So if this was a reactant of the reverse reaction, there was going to be a sharp increase in the reverse reaction. So all you have to do is, if there is an increase in concentration of something, you have to find out it is a reactant of which reaction. So this is a reactant of the forward reaction, so therefore there's going to be a sharp rise in the forward reaction. And every time there's a sharp rise, it's always going to go down up until some midpoint, something like that, right? And then this one will now, so up until a new equilibrium is established, so this one will now have to rise until it catches up with that. So therefore this will now have to rise until it catches up with that, right? So then we now have a new equilibrium being established. So this is what we have. So a new equilibrium is established. What if there was, let's create another situation. So let's see if you will get it correct. So let's do this. So let's do this. Okay, so now let's say instead of increasing the concentration of P, we have just decreased the concentration. Okay, let's just do this. I want to do all examples. Let's decrease the concentration of maybe of A, right? So if we decrease the concentration of A, I want you to pause the video and try it out. Let's see how the graph will look like. So if we decrease the concentration of A, we have to find out A is a reactant of which reaction. So A is a reactant of the forward reaction, therefore there's going to be a sharp decrease in the forward reaction. So there's always a sharp increase or sharp decrease based on which one is the compound they're reacted of, right? Is it the reactant of the forward reaction or the reverse reaction? So since this is a reactant of the forward reaction, then there's going to be a sharp decrease in the forward reaction because we have decreased, right, the reactant. So then every time there's a sharp decrease, there's always going to be a rise up until some midpoint, something like that, right? And then this one has to now catch up to it. So therefore this will start decreasing up until it catches up to it. So something like that. So up until a new equilibrium is established. So yeah, something like that. Let's just try one more time. So something like that. So up until a new equilibrium is established. Okay, so now let's go for another example pertaining to this. So let's just say instead of decreasing A, I have just decided to, let's do this. So let's just say instead of decreasing A, I just decide to increase D. So you can pause the video and try it out. You can try it out. So now let's find out, this is a reactant of which reaction? This is a reactant of the reverse reaction, because in the reverse reaction, these are reactants and these are the products. So because there is a sharp rise, it means that in the reverse reaction, since it's a reactant of the reverse reaction, there is going to be a sharp rise. So in the reverse reaction, there should be a sharp rise. So we are going to have a sharp rise in this reaction. So a sharp rise. By the way, these gaps are supposed to be closed, right? They are supposed to be exactly equal. But usually and I also represented them in different colors, but in past papers they like putting the forward reaction in solid line and the reverse reaction in dotted line to differentiate, right? But because we've got colors, we just use colors. So this is what we have, right? So there's going to be a sharp rise in the reverse reaction because this is a reactant of the reverse reaction. So now this, every time there's a sharp rise, it's going to go back down, right? Something like that. Okay, so let's try it one more time. Something like that. right? And then up until a new equilibrium is established, and then the blue one will now have to catch up to it. So this is what we will have, something like that. So something like that. So a new equilibrium would have been established, right? So something like that. So a new equilibrium will be established. Now let's give one more example pertaining to concentration, then we move on to a completely different stuff. So let's say I instead decide to decrease the concentration of C. So you can pause the video and try it out. So you have to find out this is a reactant of which reaction. So this is a reactant of the reverse reaction. So since there's a decrease in that, it means there's going to be a decrease in there's going to be a sharp decrease in the reverse reaction because this is a reactant of the reverse reaction. So we have a sharp decrease in the reverse reaction because C is the reactant for the reverse reaction, and every time there is a sharp increase, there's going to be an increase. Every time there's a sharp decrease, there's going to be an increase, right? So something like that up until a new equilibrium is established. So something like that. And then the other one will now have to catch up to it. So something like that is going to catch up to it. So something like that. And then we're going to have an equilibrium. Alright, great. So now let's go forward. Let's talk about temperature this time. Alright, so here's what you have to do. All you have to remember about temperature is notice that increase in temperature favors the endothermic reaction. So when it comes to the reaction, no matter what, when it comes to the reaction graph, this is different from the concentration and number of moles graph, right? Whenever it comes to the reaction graph, what you have to remember is that the endothermic reaction is always affected the most, right? So let's talk about it. Let's say we have decided to increase the temperature, right? So we decided to increase the temperature. So you have to find out which one is the endothermic reaction, all right? So the forward reaction is exothermic because the enthalpy is negative, right? So it means the reverse is endothermic. So because the endothermic is the reverse, it means that the one that is white, the reverse reaction, right? The reverse reaction has to have a sharp rise because we have increased the temperature. So therefore, the reaction rate will have a sharp rise. So now I want you to understand something. I want you to understand that when we increase temperature, the kinetic energy of particles increase. So both of them actually do get affected in terms of rate when we increase temperature. So in the concentration graph, both of them get affected when we increase pressure, right? All of them get affected when we increase pressure because we're decreasing the volume, thereby increasing the concentration immediately for everything, right? But in the rates part, this time the temperature is the temperature is the one that affects both the rate of the forward and the reverse reaction, right? Because the rate of everything will now increase since the kinetic energy is increased. So just remember, in concentration, increase in pressure, everything is affected, right? But in the rate graph, increase in temperature, that's where everything is affected. So both of them are affected, but the one that will be affected the most is the endothermic reaction. So that's what you have to remember. So every time there's a sharp increase, there's always going to be a decrease up until some midpoint. So it's going to decrease up until some middle value somewhere there, something like that, right? So this is what we're going to have. And then the other one will now have to catch up to it. So first of all, we're going to have an equilibrium here. So this is going to be horizontal. And then this one will now have to catch up to it. So something like that. So this is what we'll have. So up until a new equilibrium is established. Alright, great. So this is it. So now let's talk about decrease in temperature. It might be new to you, but let's see what you will do. So let's just reverse this process. So now let's say temperature has been decreased, right? You can pause the video and try it out. Let's see how the graph will look like. So when we decrease temperature, remember, both of them are going to get affected. So when there is a decrease in temperature, the endothermic reaction is still affected the most, but it will be the one that will decrease the most, right? So there's going to be a decrease in both of them initially, right? So we've got a decrease in both of them initially. But the one that will decrease the most is the endothermic reaction. Which one is the endothermic reaction? The endothermic reaction is the reverse reaction, right? So therefore, there has to be a sharp decrease at the reverse reaction. So something like that. Okay, fine. I mean, there is a sharp decrease at the reverse reaction, right? This is the reverse reaction, the one in white. So we are going to have something like this, a sharp decrease. But when there's a sharp decrease, there is also an increase, right? So it will increase up until a new equilibrium is established. So this is what we'll have. So something like that, something like this. Right, so now there's going to be straight lines because a new equilibrium has been established. Okay, so something like this. Alright, let me see if I can reverse the process because I want to just use the previous one where the temperature was increased. Let me see if I can reverse the process. Let's see, is it possible? No, it's not possible. So this is what we have. Alright, so now, okay, fine. So I just redo it. So let's talk about something. So now you know concentration, now you know temperature. Let's talk about pressure. So what does pressure do to the rate of the reactions? Okay, matter of fact, this is completely wrong. It's completely wrong because there is supposed to be a sharp increase first in both of them, but the one that is affected the most is the endothermic reaction, which is the um, the reversed reaction. So it's completely wrong. Alright, so this is the correct graph, right? So because the one that is affected the most is the endothermic reaction, which is the reverse reaction, right? And also both of them have to be affected by temperature, both the forward and the reverse reaction. So now let's talk about something completely different, pressure. So what happens if we increase the pressure in the rate graph, right? So if we increase pressure, we know pressure favors the one with the lower number of moles. So here's the trick when it comes to pressure. Because increasing pressure favors the one with the lower number of moles, what you'll always do is that the one with the lower number of moles is the one that will get affected the most, right? Whether a sharp increase or a sharp decrease. So if you increase pressure, the forward reaction is the one that produces the lower number of moles. So it will be the one. Okay, so it's the one that will increase. Something like that, right? So we don't have both of them increasing, right? Only temperature affects both of them in a way, not really on the temperature. I'll show you one more thing. But concentration and so increasing the concentration of one side obviously does not affect both of them, right? And also increasing the pressure does not affect both of them. So temperature rather, only temperature in whatever I've showed you increases or decreases both the reverse and forward reaction. So when there is a sharp increase, there is always going to be that steady decrease up until a certain midpoint. So something like that, and then a new equilibrium will be established. So then as for pressure, so because of pressure, so now notice this is actually going to have to catch up, right? It always happens, right? Always happens. So this is what we're going to have. Come on, something like that. So therefore, if you see one of them having a sharp increase and the other one has to catch up, and this is the rates graph, right, where both of them meet, right, because the rate of the forward and reverse reaction have to be equal since this is dynamic equilibrium. So whenever you see this situation, you can't really tell whether it's temperature or concentration. They'll have to specify. They have to give you more details, right? But if you see this, both of them increasing or both of them decreasing like this, you know it's pressure. So let's talk about another thing. Let's just say we instead decrease the temperature. So you can pause the video and try it out. Let's say we decreased temperature instead. So if we decrease temperature, if we decrease pressure rather, apologies. So pause the video and make sure you try it out. So if we decrease pressure, right, we know that the number of moles, the one with the lower number of moles will be affected the most still, right? So the one with the lower number of moles will decrease the most. So the the forward reaction is the one that produces the lower number of moles. So decreasing pressure, the forward reaction has to reduce. So the one with the lower number of moles have to decrease the most, right? So decreasing, I mean, what did I just say? We have decreased pressure, right? So if we decrease pressure, matter of fact, there is no mistake in my statement. When we increase pressure, the one with the lower number of moles have to increase. When we decrease pressure, the one with the lower number of moles has to decrease the most. So, which is the uh, the reverse reaction, rather the forward reaction. So the one with the lower number of moles has to decrease the most. So it has to decrease, not the most, because both of them won't be affected in that way. So there is going to be a steady increase up to the midpoint, so something like that. And we're also going to have a new equilibrium being established, so something like that. Okay, yeah, so something like that. Whilst here we're going to, this will have to catch up, right? So something like that. So it has to catch up to this one. So this is what we're going to have up until a new equilibrium is now established. So this is what we have. So something like that. So this is how it is. You can always memorize it, right? That when we increase pressure, the one with the lower number of moles will have a sharp increase. When we decrease pressure, the one with the lower number of moles will have a sharp decrease. So this is the rule of pressure when it comes to the rates graph, right? If we want to try and make sense of it, notice that if we from the rates graph, we can immediately see which one is favored, right? So notice that when we decrease pressure, notice something. Notice that the rate of the forward reaction, the reverse reaction, the one that is in white, is higher than the rate of the forward reaction, the one that is in blue, right? So it shows that the reverse reaction is the one that is favored, the one that produced the higher number of moles, right? So notice, because immediately from that change, when it comes to rate, we can see which one is favored. But always remember, these are the rules, nothing difficult, right? So I'm gonna summarize everything, but before I do that, let's talk about one more thing: catalyst. So what does a catalyst do? Alright, so now because I didn't put enough space, let me just say at T7.5, yeah, let's just say that T7.5, I decide to add a catalyst. What does a catalyst do? A catalyst increases the rate of the reaction, right? So it makes the reaction happen faster, right? So if they say catalyst, they're actually telling you it's a positive catalyst. If they say negative catalyst, then it's the one that decreases the rate of reaction. So if they just say catalyst, we know it's a positive catalyst. So if a catalyst is added, which is a positive catalyst, they will both literally increase. It literally affects both the rate of the forward and the reverse reaction. So in concentration, the catalyst does nothing, but in rates, the catalyst increases the rate of both the forward and reverse reaction. So we're going to have something like this. So they're both going to increase, and then a new equilibrium will be reached, literally something like that. So literally, so that's what a catalyst does, right? That's what a positive catalyst does. Now let's just say it was a negative catalyst. Well, if it was a negative catalyst, we would have both of them decreasing. So let's do this. So we would have had them like that. It would have decreased, right? So something like that. Okay, let's just try one more time. So something like that. So something, okay, not cool. So something like that. So yeah, something like that. So that's what we have. All right, so let's summarize this. So now, when we increase the concentration of one of them, what we have to find out is which reactant is the is that particular compound for, right? Is it the reactant of the forward reaction or the reactant of the reverse reaction? So whatever reaction that it is the reactant of will have a sharp increase or a sharp decrease. Like here we can see that there is a sharp decrease in the reverse reaction, meaning that we decreased the concentration of the reverse reaction. And then when it comes to temperature, temperature affects both of them. They'll both increase, both decrease, but the one that is the endothermic reaction will increase the most or decrease the most, right? So if we increase temperature, the endothermic reaction if we increase temperature, the endothermic reaction will increase the most, right, which is the reverse reaction. So it will increase the most, right? But if we decrease temperature, so notice something. Notice that here it's actually an increase in temperature because the endothermic reaction, which is the reverse reaction, right? Because this comes from the reverse reaction. So the endothermic reaction, which is a reverse reaction, increased the most. So that's how we can tell temperature was instead increased, right? So if we decrease temperature, then the endothermic reaction would have decreased the most, right? Both of them would decrease, but the endothermic reaction would decrease the most. Then when it comes to pressure, right? When it comes to pressure, there is no both decreasing or both increasing. It's similar to the concentration part, right? So if we increase pressure, the one with the lower number of moles will increase the most. If we decrease pressure, the one with the lower number of moles will decrease the most, right? So that's what we'll have. Yeah. So now notice that this is the reverse reaction, right? The one that produces the lower number of moles. Notice that it has been decreased the most. So meaning that the pressure has been decreased, right? So the one that produces the lower number of moles will be decreased the most. When it comes to a catalyst, the catalyst will increase both the rate of the forward reaction and the reverse reaction, right? If we add a positive catalyst, but if we add a negative catalyst, it will decrease the rate of both the forward and the reverse reaction. So there we have it.